second. Okay. So I'm going to really quickly go over the do now. So the do now, the first question was to find the average rate of change of g of t between t1 and t equals 3. So just to hopefully to represent this graphically, remember the average rate of change again is, it's almost like a really bad approximation of rate of change. So let's say we have a graph that's a parabola, right? And we want to find the average rate of change from this point to this point. Literally what we would do is find where that point is on the graph. So here, and then this point would be like over here, and then connect the two lines, connect the 2 points, right? And then this is the slope of this line right here. I'm not a good estimate it. So like this slope basically tells us the average rate of change from, sorry, it says my internet connection is unstable. Hopefully that changes. But yeah, so sorry about that, guys. Oh, there's a ton of there's a huge dip. We don't really care about that. All we care about is this average rate of change. So how do we go about that? So we basically have the change in y. And then we take note of the change in x. Right? The difference between the 2 points, who it is, if you understand just like your algebra and slopes and stuff. But the equation, to make it clear, is f of b minus f of a over b minus a. And this is the slope of the secant line. And I actually would like everyone to have these problems in their notes. You don't have to have this graph or anything. A lot of times I will visually just try to make things clear, but usually that's super messy. So I don't expect you to when I'm doing that to have those notes in there. But I would like everyone to have this problem if they haven't already written it for the do now. So just so people can copy that down, I'm going to give everyone 10 seconds to copy down everything. Okay, cool. So then we're going to plug in B and A. So A is going to be our earlier point. B is going to be, so A is 1, B is going to be 3. So it's going to be f of 3 minus f of 1. Right, we're plugging in 3 for B, 1 for A, over 3 minus 1. Again, B minus A, 3 minus 1. And this is equal to, let me take a look at my notes really quick. So I don't okay, so here, all right. So f of 3 is equal to 3 times 3 squared plus 6 is equal to, so 3 cubed plus 6 is 27 plus 6 is 33. And then f of 1 is equal to 3 plus 6 is equal to 9. So we get 33 minus 9 over 3 minus 1 equal to 24 over 2, 12. So, I mean, the calculations don't matter too much, but the general idea of finding f of b minus f of a over b minus a and understanding that this is the same as f of b minus f of a over b minus a is the same as change in y over a change in x. That's really what we're looking at for the average rate of change for rise over run for the secant line. It's the same idea. So I'll give maybe 15 more seconds to copy this down. Okay, so the instantaneous rate of change, this is the derivative. So that's what we have to remember. Anything that's instant, that's the derivative. And that is basically what we dealt with in Calc A. This is the key, instantaneous rate of change. This is like all of Calc A. This average rate of change stuff is like extremely basic, what we learned before we tackle calculus. Instantaneous rate of change is g prime of t, right? And g prime of t, we can just use power rule for 3t squared is equal to 6t. The power rule for 6 is going to be 0. That's 0, right? So we're not going to include anything. So g prime of t is simply 6t. We're going to plug in t equals 2. So g prime of t, g prime of 2 is equal to times 2 is equal to 12. So this is totally a coincidence that both of our answers were 12, but they happen to be 12, so that is great. Remember, instantaneous rate of change is we're simply finding the derivative and then plugging in our point for whatever our point of interest is. So if we wanted to find what the instantaneous rate of change at 100 is, we could literally just plug in 100 into here, and we would see that it'd be 600. If we wanted to find it, what it is at like negative 2.7, we can plug in negative 2.7. So that's what the derivative tells us. It tells us the instantaneous rate of change at any one of those points. Okay, so I'm going to give just 10 more seconds. And then, okay, so we're going to move on to our next topic, which is related. Is related rate something you guys tackled in depth in your last class, your previous class? Like something you guys went over, or is this mostly new? Okay. I'm getting 2 answers so far. Thanks, Mercy and Kayla, saying that it seems like it's mostly new. Have you guys heard the term related rates? Can I get just a few more answers? New. Okay. Okay. Gotcha. Okay. Well, okay. So just so everyone knows, I will say I think related rates is one of the more difficult topics in Calc A. Or I'm not even sure exactly if I think it's in Calc A, but that's why we're going to spend a couple days on this. And I think doing practice problems is the most useful part of related rates. I would say it is the most like interesting in that we actually get to solve like semi-real world problems. But yeah, just so people are prepared, it is one of the more difficult topics. So I'm going to provide, because of that, I'm going to provide just like a kind of a brief example of what related rates really is. Okay. So I'll start with imagining that we're inflating a balloon that is a perfect sphere. Okay, so we start with the balloon. That's a perfect sphere, right? It's just a ball. And then we're inflating it so that over time, let's say this is the balloon at 1 minute. We're inflating it so that the balloon at, let's say, 5 minutes is going to be larger, right? That's a bad circle, but it's going to be larger, but also a ball, right? A perfect ball. And let's say we're curious about the rate at which the volume of the balloon is increasing. So obviously there's some rate we can say the rate is dV over dt, although that's not that important yet. Don't worry about this. But basically the volume is increasing at a specific rate. It could be like 2 liters per minute, something like that. The volume is increasing. So I'll say there's a volume 1 and there's a volume 2. And also the rate at which the radius of the balloon is also increasing. And that just makes sense, right? The radius here is smaller and then the radius here is larger. So both the radius and the volume are increasing. And the point is, basically the rates at which they're increasing are related. So that's what related rates means. The rate at which the volume is increasing is related to the rate at which the radius is increasing. So the idea is basically if we know the rate at which either volume or the radius, one of these is increasing, we can calculate for the other. Oh, sorry, Derek just asked a good question. So I would say this part, you don't have to write this down. What's more important here is that you just understand conceptually like the types of problems that we're dealing with. So yeah, you don't have to write all that down. Whatever helps you understand what we're dealing with here. So the idea is that let's say for this ball, I have a pump, right? And I can tell how much air I'm putting into it. So I can tell the volume, right, that I'm putting into it. So in this case, because I know the volume and I know that rate and I can relate it to R, I can tell how much the radius is increasing, even though I'm not actually measuring the radius. So I'm just looking at this ball, I'm pumping in air, and I can actually tell how much the radius is increasing without measuring it at every step. And that's like the idea of related rates, is that because there are two separate variables that are related, we can kind of calculate one based off the other. But it might be a bit harder than people think. So I'm gonna give everyone 15 seconds. You don't have to write this down, but whatever you do want to write down, you can go ahead and do that and kind of like try to internalize the idea of related rates. I will also say related rates, you'll be surprised, like they're not as simple as just like a ball increasing. I think they're pretty simple, but they can vary in a lot of different ways. Murphy asked a great question. Are related rates always with volume and radius or other variables too? No, it can be a lot of other variables, which I think might be what is kind of confusing at the start, but it's actually not that hard. So it's like hard, but also like, it's like with anything, it's hard, but once you know how to do it, it's really not that hard. But no, to answer your question, it goes much beyond like volume. Okay, cool. So I think the best way to do this is we are just gonna tackle our first related rates problem and just go straight into example problem. So I'm actually gonna cold call for someone to just please come off mute and just read this problem out loud so we can kind of try to understand it. Zakaya, could you please come off mute and read out the problem?
A 5-meter ladder leans against a wall. The bottom of the ladder is 1.5 meters from the wall at a time t equals 1 and slides away from the wall at a rate of 0.8 meters per second. Find the velocity of the top of the ladder at a time t equals 1.
Awesome, thank you, Zakaya. So obviously, just even me reading that, I'm like, what the hell? Like, that's a lot. I can't even like visualize this just right away. Like, I don't know what I need to start with. So I think with related rates problems, the first step that can be very helpful is just drawing a picture. So we have a wall, right? let's say a wall, this is the ground, and we have a 5-meter ladder that is leaning against the wall. So this ladder is 5 meters. Right, I'll just write 5 for now, just so it's not as cluttered. Right, this ladder is 5. And I would like, actually, I'm gonna give everyone like 30 seconds to a minute just to copy down the problem. If you wanna like kind of shorthand it and not write down every single word, that's fine, but I would like for everyone to copy down the problem in their notebook. So yeah, I'll give everyone a minute for that. Okay, cool. So we're gonna try to draw this problem out. So we have a ladder that's leaning against a wall, right? And the ladder is 5 meters long. That's cool, that's pretty easy to understand. The bottom of the ladder is also 1.5 meters from the wall at the time t equals 1. So that means the distance from the bottom of the ladder to the wall is 1.5. So that's also great. That gives us this value right here. And this is time t equals 1. Let's just write that down. And the ladder is kind of sliding down, right? So you can imagine the ladder's like, this part's falling, this side of the ladder is going this way, right? You can kind of imagine the ladder sliding down. What we are told is that the bottom of the ladder from the wall, it slides away from the wall at a rate of 0.8 meters per second. So basically this bottom of the ladder is going in this direction at 0.8. I'm going to write this out as rate. So 0.8 meters per second. Find the velocity of the top of the ladder at times t equals 1. At time t equals 1. Okay, so we need to find basically the speed at which the top of the ladder is going down, because we know this is going down. So we need to find what this rate is. So it's like a certain meters per second, but we don't know what that is. So this is kind of different from that volume problem, the related rates example I gave, right? But they are actually all related. So let's start with, I think after we draw a related rates problem, the next best step is to start off by clarifying what values we know and what values we don't. So I'm going to separate these values by what do we want to know and what do we already know. So it's easy to start out with what we want to know. So here, I'm going to label each of these sides also as y, x, and then I'm going to label this as r, just so we have each of these sides figured out. So what we want to know is the rate at which y is decreasing, basically, right? Because y is this distance from the top of the ladder to the bottom. X is the distance from the wall to the bottom of the ladder, right? So for y, our rate is going to be dy over dt, right? Because this is the rate that y changes with respect to time. So this is the rate that we want to know, dy over dt. What we already know, so we can start off with what rate we already know. We know that dx over dt This is the rate at which x is changing. We're given this. So dx over dt is 0.8 meters per second. So that's fantastic. That makes things a bit less confusing. We also know that r, right, is equal to 5. Right, we see that here. And then x is equal to 1.5. So the rate for x, dx over dt is 0.8, but x itself is 0.5, right? One thing I'll say we can also calculate for is, we know that this is a right triangle, right? So we can calculate for y, so that might be helpful. So I'll just quickly show that we can calculate for it. Here I'll put, so we know that x squared plus y squared is equal to r squared. This is literally just Pythagorean theorem, right? Because we have a right triangle. X is 1.5 squared plus y squared is equal to 5 squared. I have this already solved, but basically y is equal to, yeah, I'll just write this over here. Y is equal to 4.77. Now, and then, yeah, so here, I'll just make that more clear. Y is equal to, what was that? 5 squared minus 1.5 squared square root. And then if you solve for this, you get y equals 4.77. Okay, so these are basically all the values we know. And we want to find dy over dt. Great. So the next question is, we already figured out our rates, right? We looked at what rates we know. And then the next part of related rates is, well, the related part. So how, I'll say what equation relates what we know. So we already have like x, y, r, like all these values, but how do we put them all into one equation so we can actually solve for something, right? And the answer when we look at a right triangle is the most obvious answer, which we already used, which is the Pythagorean theorem. We can relate all three sides. We can relate x, y, and r using the Pythagorean theorem. So I'm going to write x squared plus y squared equals r squared. So that's great. We have all these values related, at least the three sides. But now we got to move on to what we notice probably is that you're missing, even though we have like these values, but we don't have dy over dt. We don't have dx over dt. We don't have the actual rates. So next question would be, how do we incorporate okay, that is too many. Incorporate rates. Ansel, you said you have a question. Do you want to come off mute and ask the question?
Yeah, for the variables that you gave for these, can you choose like any random variable, or is this part of like a specific equation that you gotta use?
Are you talking about x, y, and r?
Yeah.
Like which? Oh, I mean, you can name these whatever you want. So this could be A, B, C, whatever, X, Y, Z, whatever you want. But the end equation, like x squared plus y squared equals r squared, that is the Pythagorean theorem. So you could replace that with a squared plus b squared equals c squared, whatever x squared plus y squared equals z squared. So the variable names don't actually matter, if that's what you're asking.
Yeah, that was it.
Okay. Okay, so how do we incorporate rates, right? We have dy over dt and dx over dt. That's what we're really curious about, right? Dy over dt is this is our answer, right? We're trying to find this. So derivatives, this is where like the calc A part really, sorry, it says my internet connection is unstable, so I'll keep it 10 seconds. Okay. Anyway, so we're incorporating derivatives. And basically, we're going to start using implicit differentiation, a skill that we learned, which is very useful. So we're going to write x squared plus y squared equals r squared d over dt, d over dt, right? So we're finding all of these as rates with respect to time. Instead of state right now is x squared 1.5, but that doesn't tell us. So again, with implicit differentiation, remember how we did before where it's chain rule? Hey guys, sorry, I don't know what exactly went wrong, but wait, can you guys all see/hear me? Okay. Okay, cool. Not sure if you guys were all kicked out of the Zoom room, but I was for a second. Okay, anyway, hopefully everyone is back. I'm just gonna continue. So we're gonna differentiate this all with respect to time. So with implicit differentiation, remember that we're differentiating with respect to a different variable. So we're not differentiating with respect to x, right? It's not d over dx. If it was, we could just do 2x and then we're done. But we're differentiating with respect to t, so we're actually going to get 2x, and then we have to remember to multiply by dx over dt. Remember, it's a mini chain rule, so we're multiplying dx by dt. And then also the same thing happens with y squared. So we're going to do power rule, so 2y, but we're not done. So we have to multiply by dy over dt. Dy over dt this time equals the same deal with r squared. So we're going to get 2r, cool, but we're not done. We need dr over dt. Right? So now we have this equation where we differentiated this with respect to time. It's the same type of equation. We differentiated with respect to time, and then now we incorporated these rates. And this is where it's useful. So just before we move on to the next step, notice we can cancel out 2 in every single component. So our final step is just plug in values and solve. I'm going to give everyone 10, 15 seconds just to catch up on anything they have to write. Okay, cool. So we're just going to plug in values. I'm going to rewrite the equation. So x times dx over dt. Remember, we don't need to include the 2 plus y, dy over dt equals r, dr over dt. So let's just plug stuff in. Remember, x is 1.5, right? So we're going to have 1.5 dx over dt, which is the rate at which x is changing over here, right, is 0.8. We clarified that over here, it's 0.8. Oh, sorry. Okay, so we're just gonna multiply this by 0.8. I'm gonna minimize this for a bit. Okay, so 0.8 plus y is 4.77. We calculated for that. dy over dt, which is the rate at which y is changing. Well, that's our answer. That's what we're looking for. So it makes sense. We're going to not have that. We're going to solve for it. So dy over dt equals r. Our r is 5. And then this might be kind of confusing, but I would like some people to participate in chat. What do you guys think dr over dt is? So it'd be the rate at which r is changing, if you think about it in that sense. So if anyone wants to just chime in the chat. Okay, Samantha said 2 pi. Can I get a few more thoughts on what dr over dt would be? Mercy said, would you add dx and dy? Okay, so I'll just kind of clarify this. This can be kind of confusing. So I think it's helpful to think about these questions just like, Aaliyah, you raised your hand. Do you have something you want to add?
Oh yeah. I think it might be like the related rate equation, because I guess I don't know what D is supposed to be, but maybe R is the radius, and then I don't know about T or something like that.
Okay.
Oh, T
Yeah.
is
So thank you for volunteering. So R isn't. I just labeled this R. Maybe I could have chosen a better variable. So R has nothing to do with the radius. Just to make that clear, I just chose variable R. There's no radius here. But okay, so this is the issue I think with related rates. It's like super confusing having all this d whatever over dt stuff. So it can be kind of confusing to think about it in terms of that. So I would suggest, like, for each of these, like dx over dt, what does that really mean? It means the rate at which x is changing, right, with respect to time. So it's like 0.8 meters per second. That's the rate at which x is changing because we were told that. dy over dt is the rate at which y is changing. So this ladder is falling down, right? So this y is kind of decreasing as this ladder falls down, right? Because y is the distance from the bottom to the top of the ladder. So what is dr over dt? R is the length of the ladder. So how does the length of the ladder change over time? And the answer is it doesn't, right? The length of the ladder is always going to be 5. The ladder is not going to like shorten to like 3 meters as it falls down or anything like that. So it's always going to be 5. So that means dr over dt is actually just 0, right? Because the rate of change of r over time is 0. It doesn't change. So this is all going to be 0. So really what we have in our final equation is 1.5 times, oh wait, I'm just going to multiply that. It's 1.2 is equal, or adds 4.77 times dy over dt is equal to 0. And then that is, I'm just going to put 1.2 on the other side, standard equation stuff, dy over dt is equal to negative 1.2. And then if I just do this in a calculator, dy over dt is equal to negative 0.252. And then this is a rate, remember, so I can write meters per second. So this is our final answer. So I'm going to give everyone 10 seconds, 15 seconds to copy that down. Awesome. So what this number is really saying, negative 0.252, is just saying that this ladder is falling down we see this ladder is going to the right at 0.8, right? This ladder is now falling down at 0.252 meters per second. So you can kind of visualize that. Yeah, I don't know, like, hopefully you guys can visualize that as this ladder is like kind of sliding down. The bottom is going out relatively fast and the top is going down slower at t equals 1 at least. And yeah, I mean, that's our answer. And the steps we took, it looks like it's a lot of work, but really it's not, I would say it's not that difficult in the sense we just kind of figure out what we already know, what we want to know, and then we find our one equation of interest. Now this is the key equation, and identifying this equation is very important. In every problem, the equation is going to be different. So for example, in this volume problem, we're obviously not going to use the Pythagorean theorem. We'd have to somehow use the volume formula for a sphere, which I think is like 4/3 pi r cubed. And then we know v, right? So through this equation, you notice we have v, you notice we have r. Now we can relate v and r. We just have to do our differentiation. We just have to do the whole dv over dt, dr over dt, do all that implicit differentiation, and then we can find our answer pretty easily. So identifying that equation is very key. So there's only 2 minutes left. I don't have anything else to add. The exit ticket problem today is just straight up a related rates problem. So it might be kind of difficult. I would like for everyone to give it their best shot. Of course, if like I understand it might be really difficult the first day. I will say the related rates problem is pretty similar to the example problem that we did in class. There are subtle changes, but it does utilize the same Pythagorean theorem. So it is a triangle related rates problem kind of. But yeah, that is it. I will stay after class for questions. Remember to turn in the exit ticket by 10 p.m., class notes by 10 p.m., all the usual stuff. And then don't forget to keep working on your homework packet. That will be due Friday night. But that is it. Thank you all for coming, and I'll see you all tomorrow. Mateen, I see you have your hand raised. You can go ahead and unmute yourself if you have a question.
Yeah, I wanted to ask a question. Right there where it says on 2x parentheses, dx over dt, yeah, that whole situation right there.
Right here?
Where did the
Okay.
terms get cancel out to?
Sorry, did you say where did the 2's cancel out to?
Yeah, like why did they cancel out?
So the 2's just cancel out just because it's like, let's say 2x equals 2y, right? We can divide both sides by 2. So then we just get x equals y. Does that make sense?
Yeah, and then all the information that we got in there already know, we just plugged it in for like plug-in values and so.
Yeah, so I canceled out all the 2's and we came up with this equation right here. And then using this equation, yeah, we just plugged in the values that we already know.
Okay, I understand that. Thank you.
Okay, thanks. Zakiya, go ahead.
I have a question for when it's at the equal sign. Why did you put 0? Hello.
Sorry, which equal sign?
The first one. When you put the 0, why did you put it 0?
Oh, wait, right here. So do you understand why, sorry, my internet connection is kind of bad. Do you understand why dr over dt would be equal to 0?
R over dt. No.
Okay, so, do you understand this part of the equation, the 1.5?
Yes.
Okay, yeah, so I'm just kind of filling in an equation again. So we know, so the right side, we know what R is, right? R is
It's 5.
5, right?
Mm-hmm.
Now we have to multiply by dr over dt. Now dr over dt is kind of confusing because we don't have it over here, right? You're looking at what we already know, we don't have it. So we kind of have to figure it out, but it's actually not as confusing as it seems. So dr over dt is just the rate at which R is changing. So R is the length of this ladder, right?
Okay.
But yeah, R, it's a ladder, right? So it's going to stay 5 no matter what. It's not changing, if that makes sense. So it's going to be 0. And then you multiply 0 by 5. So obviously then that's
And
0.
so if it changed, say it went from like a 5-inch meter ladder to a 2, then you put the 2 in that space?
Well, so that'd be really confusing. That'd be a really weird problem, but they would have to tell us that. They would have to say like the ladder like shortens at a rate of at a rate of 2 meters per second.
Mm-hmm.
So it decreases at a rate of 2 meters per second. And then actually in that case, if they told us that, then it'd be -2. So it's decreasing.
Okay.
But yeah, we would multiply by -2. But like, yeah, I don't think that would happen just like for this type of problem. But yes, they would have to tell us that information. Like there would be no way for us to calculate that ourselves.
Okay.
Right? That would be, yeah.
Okay. Thank you.
Okay, yep, thanks. Have a good day.